All right, a critical point is where your derivative is 0 or undefined. So where your derivative is 0 or undefined. And remember, a derivative is a slope, a rate of change. Remember Alice going for a walk? Rates of change, slope, miles per hour. It's always something per something else. So if you have a 0 slope, what kind of a line have you got? Horizontal, flat line. Okay, so let's draw a few pictures of what that could look like. This could be a horizontal tangent. Oh my gosh, and I remembered to wear my shirt today. Prepared this morning. All right, or your graph could go like this and you'd have a horizontal tangent line. Or you can have something like a cubic graph, and you can have a horizontal tangent line in there even though the graph doesn't change direction, and we'll talk more about that in a second. But those would all be places on the graph where the slope is 0. Undefined would be like an absolute value graph where you have that sharp edge. Can you get a slope at that point? No. This slope is -1, this slope is +1. Like it's not a nice smooth curve, so you can't get a slope at that particular point, right? So 0 or undefined, critical point. If your function is increasing, your derivative, oh good, is positive, or I say above sea level. Again, please don't write because the derivative is above sea level on a test. They will not take that on the AP exam. You have to say is positive, but that's what I call it, just to get everyone to remember it. Yeah, or greater than 0 with the little alligator mouse or your little inequality symbol, that's fine too. All right, if your function is decreasing, that means your derivative is negative or less than 0 below sea level, but don't write that on the test, okay? So what I always do is color code the places where we're increasing or decreasing. So looking at this first one, where is our critical point? It's at x equals what? 0. And we're going to label it as a relative minimum, maximum, or neither. So this is a relative minimum, good, at x equals 0. Okay, cool. We might be able to stay on track. This is going quick because you guys are all understanding. Relative minimum at x equals 0. Draw yourself a little grid over here to graph your derivative. And that is the only specific point you can put on your derivative graph is at 0, 0. Everything else will be good enough. So if you're a very like type A person and everything has to be perfect, I need for you to take a few deep breaths and just understand it's not going to be perfect. It's going to be good enough. Okay. So I'm going to highlight my decreasing part blue. So decreasing, that's where I want my derivative graph to be negative or below sea level. And then I'm going to color code my increasing part purple. And that's where I want my derivative graph to be positive or above sea level, greater than 0, however you guys want to say it. So all you have to do is draw something that goes through this point and is below and then above. You want to be below and then above. So something like that. Do you see how it's below the x-axis and then above? Okay. Try another one. That's all that there is to it. Okay? Which actually, for the sake of time, let's skip 2 and go to number 3. I always put more on here than you really need. We'll do number 3. Yeah, 3 is a little bit more wiggly. So where do we have a critical point? There's a few of them. I don't really care what order we say them in. What do you think? -2. Now, is that the location of a relative maximum, minimum, or neither? Yeah, neither. Okay, so neither at x equals -2. But it's still a critical point. So when you go to graph your derivative, you can put that 0 at -2. Correct, it will. Because we don't have a change there. So I put that 0 at -2. And again, those are like the only specific points you get. Everything else is like, good enough. Right? So where is there another one? 1, good. Relative maximum or minimum? Maximum. So relative maximum, you guys okay? At x equals 1. And so you can put a 0 at 1. And again, the reason these are zeros is, do you see how the slope is 0 at that point? I'm drawing in the horizontal tangent line so you can see that there's 0. Like visually, you can see that that's 0. All right, and then there's one more. 3. we have a relative minimum at x equals 3. So we can put a 0 at 3 on our derivative graph. So again, those 3 points are specific. Everything else is going to be like good enough. So I'm going to highlight my decreasing part. I'm going to stick with blue. So decreasing, that's going to be negative or below the x-axis. All of the rest of this is increasing, which is where we're going to be above the x-axis. It's like little positives and negatives, like a battery. I always think of like batteries when I do this, the positives and the negatives. So you want to be above, above, below, above. Do you see that? The colors help. Above, above, below, above, and go through those 3 points. So you're playing connect the dots, but just doing those things. So if you want to watch me do it first, you can. We're going to be above, stay above, because there's not a change there. Connect to the next one, go below just for that short piece. So below and then above. How far up does this go? No idea. How far down does this go? No idea. It is good enough. The only specific points we got are the zeros. Okay. Critical point is where for this one? 0. So we have a relative minimum at x equals 0. Unfortunately, you can put precisely nothing on your derivative graph. Why can't we put a point at 0? Yeah, instead of being 0, it's begins with a U. Undefined, undefined. So you can put precisely nothing on there, right? We are decreasing, so we want to be below, and then increasing, so we want to be above. Now, all of the rest of these, it was like, good enough. Because each part of an absolute value graph is linear, you actually can get those slopes exactly. If this is your parent graph, like it wasn't stretched or shrunk, nothing weird happened, what's the slope of this? Negative, watch me do this. We're going to be at -1 until we get to 0. I put an open circle because undefined. You can't get a point there. Oh my gosh, it's almost like I tricked you into learning this already. What's the slope of this side? 1. So you're going to be at +1 and go this way. Those graphs are derivatives of absolute value. You'll notice after you get to know me a while, I love to do that. Trick you into learning something before we already get there. And then when we get there, you're like, oh, I already know this. Yeah, good.
Are either of them filled in houses?
No, you cannot get a point there because undefined. There is no derivative at 0 because of the sharp edge.
Where the point at 0, 0?
Correct. There's nothing there. Undefined means you cannot get a point there. It's just missing. Good questions. All right, what is this the graph of? Exponential, e to the x. Does anyone know what about e is? Because this is a number. If you know it is around 2, it's 2.718 ... I only know that because I'm a calculus teacher. No, ln, but I'm glad you're thinking that. Ln it's on its side. Ln has the vertical asymptote and it goes like this way. But they do look almost the same. It's just turned on its side. The way I remember E, you know, a capital letter E has, for what it's worth, if this helps you remember it, for exponential, you know how a capital letter E has all of these horizontal parts of it? Mm-hmm. Exponential has a horizontal asymptote. And logarithmic, the letter L is literally a vertical line. Logarithmic has a vertical asymptote. Cool. You guys do that a lot. Okay. There are no critical points. This doesn't ever actually go 0, and it's never undefined. So no critical points. Cool. And also, what is it doing all the time? Yeah, increasing. So we want to be positive all the time. So when you draw the derivative graph of e to the x, guess what it is? E to the x. I love that. E to the x is my favorite function. It's just a swoop. Continuous, it's differentiable, it's always positive, it's its own derivative. E to the x is just the best function. I just love it. My favorite one. All right, is this the graph of sine or cosine? I know you're like having an existential crisis.
That's sine.
So the way you tell us where it starts, where does it start? 0. So it's sine. Where does cosine start? It's okay. 1. Okay. Now there are an infinite number of critical points for this, so I'm not going to write anything out. Like, it's going to wave forever. You're going to have an infinite number of critical points. We obviously cannot list them all out, so I'm not going to bother with that. Yeah. Okay. You can think of it that way. However it works in your mind. I just remember sine starts at 0. That's how I remember it. Each tick mark is pi over 2. And so our first 0 right here that I'm pointing at, this 0 slope, that's going to happen at pi over 2. And then the next one is at 3 pi over 2. And basically it's every other. Oh my gosh, isn't that crazy? Can I get everybody else there though? So your decreasing parts is where your derivative is negative or below the x-axis. Increasing means positive or above the x-axis. And if you follow along with that, the derivative of sine is cosine. Yeah, cool. Now, if it's not exponential or a trig function, if you have a polynomial, which again, a polynomial is like x to the 7th, x to the 4th, x to the 1st, just, x by itself, x to the somethings. What happens to the degree each time you take a derivative? Yeah, it goes down by 1. And so we're going to make a list of the order that they go in. If you have a cubic graph, the derivative will be what? Squared, which is quadratic. I'm looking for a word. Right? And then derivative of quadratic, linear. Good job. Derivative of linear is constant, which is horizontal. And the derivative of a constant is 0. So eventually, if you do enough derivatives, cycle down to 0. Yeah. I wrote it as Z-E-R-O because all the rest of these are words, but you could just put a 0. That's fine. And the derivative of 0 is 0. Go on forever and ever. All right. Again, we may not do all of these for the sake of time. We'll just do enough so that we remember what's going on. So your derivative, f prime, and we went over this last time, it's limit h goes to 0. Does anyone remember? I will be very impressed, but I just want to throwing it out there. I'm going fishing. What do you think? Limit h goes to 0. I know that you know it. Just hold on a second. It's f of something. X plus h, good. F of x over. Perfect. You want to humor me and write that down? It's going to be on the AP exam. Now, what that will give you is the derivative in general. You'll have f prime of x equals x squared plus 2x plus 1, something with x's in it. If you want to jump straight to getting the derivative at a specific point, so instead of f prime of x, if you want f prime of 2, you would use this one instead. It's limit as x goes to c. C would be whatever number that is. So 2 or 7, like that would be a value. And it's f of x minus f of c over x minus c. That will show up on the free response part of the AP exam. It will be on there. I promise. But look, here's how I'll calm you down. If I cover up limit, that's just slope. y2 minus y1 over x2 minus x1. It is regular old algebra 1. It's not any different than algebra 1. You know what I'm saying? Subtract the y values, subtract the x values. Okay. So we're going to skip 7, hop down to the next one because we're going to do that again down here. Is this function continuous at 3? You would plug 3 into the first part, plug 3 into the second part, and see if they do what? Equal. They touch, if they meet up. 3 squared. 9 minus 2, 7. 3 times 2 is 6 plus 1, 7. Yes. Huzzah. They came out the same. Is the function differentiable? Now that involves limits. We're going to do limit as x approaches 3 from the left, limit x approaches 3 from the right. This is how this will show up on the free response part of your exam. And they will be like, use correct limit notation and all of that. And you'll have to write it out. So which piece of the function is from the left? Yeah, they're less than, right? The x squared minus 2. So it's the function, it's f of x. I'm following along with this right here. It's just the function minus what you get if you plug that in. We literally just did that. It was 7. Right? Over x minus c. And our c value, well, it's what you plug in to get the 7. The x part of that. So it's 3. Let's do the exact same thing from the right. It's the function, the x squared minus 2, minus whatever you get when you plug 3 in. I didn't talk us through that again because we kind of just did it. We got 7. And then it's over x minus 3. I'm about to do it again, except which piece of the function? Yeah, the 2x plus 1. And then minus what you get when you plug 3 in, which we already did it. It was 7 over x minus 3. Okay? We're going to divide and conquer. I'm going to split you guys right here. Everybody on this side do the first one. Everybody on this side do the second one. All right. I'll pause the recording. All right. Guys on this side of the room, what did you do to the numerator? It factors into what? Good. So these cancel. And then you would plug in 3. 3 plus 3, 6. Nice job. All right, guys over here. You would factor out a 2. These cancel. It doesn't even matter what you're plugging in at that point. You get 2. So is the function differentiable? What do you think? What does it feel like? Correct. Why is it no? They don't equal each other. So here's what happens. It is continuous. They meet up, but it's not differentiable. What would this look like since it's x squared? Like what shape is what I'm asking? A parabola? And then what is this? A line. It would look like that. Well, slopes are different as they meet up, okay? So a function is differentiable if, these are your rules, no discontinuities. You can abbreviate that if you want. No discontinuities, no asymptotes, no holes, no breaks, no jumps, or other emotional issues. I know. You can abbreviate DISC like this. All right. No sharp edges. So like an absolute value. No corners. Or the other thing is called a cusp. You can't have a cusp. All right. And usually those go over well. Here's the one everybody forgets about. No vertical tangent lines. Because by definition, what is the slope of a vertical line? No. Well, hold on. We need to have a totally separate conversation. Travel back. Thank you. Travel back to Algebra 1 with me. Hold on. Because I need to fix that right now. Infinity is not a slope. Infinity is not even a value. No. No. Your options for a slope are positive, negative, 0, and undefined. That's it. There are no other choices. So we're going to try one more time. By definition, the slope of a vertical line is perfect. Okay, cool. Infinity is not a number. All right. We're going to just do this first one because they all turn out kind of the same. But this is a cusp. Like how I would draw a bird flying, basically. That's what a cusp is. But we can just do the first one and that'll be fine. So is this function continuous? We're just going to talk about it. Yes. Is it continuous everywhere?
No.
Yeah. Continuous negative infinity to positive infinity. Here, let's write that. Continuous negative infinity to positive infinity. Continuous all the time. Is it differentiable everywhere? No. Where is it not differentiable? Yeah. Now, unfortunately, you can't just write that. They are going to make you use limits. It's going to say on the AP exam, use correct limit notation. You're going to have to do limit x approaches 0 from the left, limit x approaches 0 from the right. And you have to memorize the formula, but it's slope. It is regular old Algebra 1 slope. F of x minus f of 0 over x minus 0. And it's cool. I have to write that twice. Yeah, you're going to be okay. Anyone can write the same thing twice. I could bring my 13-year-old in here and tell him to write the same thing twice. He could do it. So, got to write the same thing twice. It is a formula that is just memorization. That's all it is. All right. Now, if you look at the slope from the left, what are your thoughts? Slope from the left was negative. I usually write is negative, but you guys seemed to like this better. Do you want that? Or you can write is negative. That's fine. And then slope from the right, positive. Or you could write is positive. All right. All the rest of these are going to turn out the same way. From the left, it's going to be negative. From the right, it's going to be positive, or vice versa. Okay. So let's try and match up these 13, 14, 15 here. Basically, it's going to go from the most wiggly to the least wiggly. Every time you take a derivative, you go down a degree. So A, B, or C, which one has the most twists and turns in it, do you think? Do you see how C has a turn here and here? Oh, that's blurry. Okay, so that's going to be C. Now watch me point to this, because I don't actually have a better explanation than, hey, look. Okay? Do you see how the derivative should have a 0 here at 0 and at whatever this is? The axis isn't labeled, so I don't know, 2, whatever you want to call it. So what is the derivative of C? Well, it looks like it's B. And then humor me for one more second. Do you see how B has a critical point here? And do you see how that matches up that A has a 0? That's how you link them up.